You've been practicing calculus, calculating with infinitely small values, infinitely small changes, and calculating with limits. Today we finally get to talk about something we can relate these calculus operations to. So this is our first connecting calculus to sort of a real-world application. So you remember back in chapter 2, we computed average velocity. Here I have a graph. Pretend this is distance traveled or position graphed against time. So I could find average velocity by computing change in position divided by change in time. We said that if later we wanted to talk about instantaneous velocity, what is my velocity at one single moment in time, I can perform that same calculation. I just have to let my 2 points on this graph get closer and closer together, so close that the distance between them is essentially 0. So we said I could do that by taking the limit as the change in the time goes towards 0. And you can see we have this expression here. Well, if that result of taking the limit as the change in distance divided by change in time as the change in time goes towards 0 is called velocity, and this operation we perform, that's the same as taking the derivative, that's that same math we did, this leads us to this conclusion that velocity is the derivative of position. So this goes on your notes, there's a place for it. If velocity isn't denoted with v or as v of t, and position, which is typical, is given with the function notation s of t, then velocity is the derivative of position, v of t equals s prime of t. Or if we use that other notation, v of t equals ds dt. So that's the number one most important idea to take away. Velocity is the derivative of position. Now, sometimes we get a little loose in our language, and when we really mean to talk about velocity, we use the word speed, or sometimes when we really mean to talk about speed, we use the word velocity. So let's understand the difference between them. There's a very clear difference. Velocity is speed with direction. Speed is just the absolute value of velocity, so that the magnitude of the velocity is another way that you'll learn to say it when you take physics. So velocity is one thing, it's derivative of position. Later, if you want to talk about speed, speed is the absolute value of the velocity. Oops, so let's look at that problem on your paper. What if I have a car, I know its position at time t is given by this function, t squared minus 5t plus 1. Can you write me a function that tells me the velocity of the car at any time? Well, velocity is the derivative of position. I can take the derivative of t squared minus 5t plus 1. The 2 comes to the front, and that's going to be 2t minus 5. Speed is the absolute value. Oops. I wrote it in symbols there, and I should have written in words. Speed is the absolute value of velocity. Write that out in words, and then here in notation, the velocity, the v of t function, inside absolute value bars. So I can do this example now. So in this example from right here that we just did, what is the speed of the car at time t equals 2? Well, first I have to find the velocity at time 2. I'll come over here to do that. V of 2 is, the rule is 2t minus 5, so that's going to be 2 times 2 minus 5, which makes -1. The speed of the particle at time 2 is the absolute value of the velocity, which is the absolute value of -1, which is 1. Okay, important velocity fact number 1. This is just sort of a definition. We have to understand this language when we see it, because you will see this on the AP test. A body, anything that's moving, something, a particle, anything that moves, it's at rest anytime its velocity is 0. That's the definition of rest. When the velocity is 0, whatever it is that was moving, it's at rest. So here's this problem from the multiple choice test in 1988. The particle moves along the x-axis so that its position is given by this function, x of t is t cubed minus 3t squared minus 9t plus 1. For what value or values of t is the particle at rest? Well, what did I say? It's at rest if its velocity is 0. Start by finding the velocity. Wow, that looks a little funny. Let me fix that. V of t. Make sure you're labeling these functions. I could label my answer v of t. I could label it x prime of t. It means the same thing. The derivative of position is velocity. That's going to be 3t squared minus 6t minus 9. So step 1, I found the velocity. Step 2, I need the velocity to equal 0. So 0 equals that same velocity. I'm going to write it out for your benefit. I don't expect that you would want to write it out again, because now you want to get down to the business of solving this equation. How do I solve this equation? Notice the degree of this equation is 2. Typically, our best bet for solving equations of degree 2 and higher is to use the zero product property. That means I want to get a 0 on one side and factor on the other side. That's going to be 3 times t squared minus 2t minus 3. I just remembered I have a whole slide that does this work. Now I can finish that up. I've set my velocity equal to 0. I noticed that 3 is a factor. T squared minus 2t minus 3. That's about the level of factoring you'll be expected to do on the AP test, but you'll be expected to do that. So my new equation, 3 times the quantity t minus 3 times the quantity t plus 1. The step that's not shown here is that each of those factors I'm going to now set equal to 0. So either t minus 3 equals 0 or t plus 1 equals 0. I get two solutions, t equals 3 and t equals negative 1. Why have I crossed out negative 1? Because we're going to go back to the context of the problem. I've been told that my position function is only good for, here I'll circle it, times greater than or equal to 0. So the derivative of a function is not defined anywhere the original function was not defined. So I'm removing from my set of answers any time value that was outside of the original domain for the original function. So when is this particle at rest? This body, or at whatever it is that was moving, it's at rest anytime its velocity was 0. That happens at time equals 3 seconds. Important velocity fact number 2. This is sort of the same thing. I'm going to state 3 different ways. When velocity is positive, motion is forward. Whatever forward means in your context. So if you're moving along the x-axis and velocity is positive, that's meaning you're moving toward the right, toward the positive x's. If the motion is along the y-axis, up and down, and velocity is positive, that means motion is up. So if you are leaving for school in the morning, your velocity is positive, that means you're driving toward school. So when velocity is positive, motion is forward, whatever forward means in the context. When velocity is negative, motion is backward, whatever that would mean in the context. And this is key. You will definitely see this on the AP test. Direction changes when velocity changes sign. So if positive velocity means I was going forward and negative velocity means I'm moving backward, then the moment at which I turn around, it's the moment when velocity changed from positive to negative or negative to positive, and that is velocity changing sign. So here's a question. If this is the graph of the velocity of some particle, something that's moving, at what time or times does the particle change direction? So let's check this out. My particle is going to change direction anytime velocity changes sign. Notice this picture tells me that the velocity was negative, 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 and then positive, positive, positive. So below the time axis, then above the time axis, and then below again. So there were 2 places where the velocity changed sign. What you're looking for places where the velocity was 0 for half a second, and then either switched from below to above or above to below. So that happens twice. I'm going to write up my answer using official calculus justification wording. There we go. The particle changes direction at time t equals 3 and time t equals 5 because the velocity changes sign at those times.